Good morning, everyone. Thanks for being here this morning. And before I start, I just would like to thank the organizer for including the paper in the program. I was here 3 years ago, and it's always nice to be back. And I also would like to thank Jules, because he's basically coming here just for this discussion. So thanks for being here. Let's start. So I have to be on this side. Here we go. So first of all, this is joint work with Davide, Brandeis, and Allan at San Diego. So let's start with the key observation, is that we, in general, observe high-frequency stock prices and returns, think about daily or intraday. But when we talk about cash flows, we only observe them at lower frequencies, so either quarterly or annual, okay? And what this causes is that limits our ability to estimate and test asset pricing models using high-frequency data, because we have the return series at high frequency, but we don't have any cash flow sequence at high frequency, okay? And also another issue is that to what extent high-frequency cash flow dynamics impact stock price dynamics. So we're not talking about just the mean, the expected return, but also the higher moments like jumps or volatility, okay? And how do we, as a profession, deal with this issue? Well, we tend to work with smoothed year-on-year aggregate changes in dividend earnings, okay? So we aggregate dividends earnings within a quarter, within a year. By doing that, though, so by temporarily aggregating cash flow news, we lose a lot of information. Why? Because think about that. We might have a dividend announcement in March and a dividend announcement in September, and that will have the same value once we aggregate, okay? And so we're missing out on potentially a lot of interesting features in the dynamics. So what we do here in this paper, we try to address this problem, to fix this high-frequency cash flow data problem. And how do we do it? Well, we construct the high frequency, and by high frequency in cash flow, we mean daily. That's the highest frequency possible for measuring and modeling cash flows, okay? So we construct this high frequency daily cash flow index using a new method for extracting and modeling daily cash flows. So we're looking at daily stuff here. A fact little known is that on any given day, multiple firms announce dividends or earnings, and therefore, cash flow news hit the market almost every day. So the issue is not whether cash flow news hits the market in the forms of announcement of earnings or dividends, but how can we look at the relationship between this news and reaction in stock prices. So how do we measure and model them? What we do? First, we need to measure daily cash flows. So what we do is we consider year-on-year changes in individual firms' dividend announcement on any given day. So we take a firm announcing dividends today, and we look at the same announcement of the same firm around 1 year ago, earlier from today. And we compare apple to apple, so May 5th today versus May 5th last year. Okay? And then what we do, and another important thing, we focus on announcement here. So whenever we use dividends extracted from CRISP, for example, we look at paid out dividends. Okay? The problem with that is that that's known when the dividend is going to be paid out, but the announcement is what we should really look for when addressing the impact on stock prices, like the announcement effect. So that's why we look at announcement here. And then what we do next, we average these year-on-year changes across all firms announcing dividends in any single day. So every day we will have basically an aggregation amongst firms that announce dividend that year and also announce dividend the previous year. This is called a bottom-up approach because we start from the firm, individual firms. And the nice thing about this is that this accounts for firm-level heterogeneity, so kind of firm fixed effect, okay? And of course, this is nice, but also the resulting series is very noisy and contains some outliers. And we will see some graphs in a bit. And therefore, we need to find a way of dealing with this kind of structure of the series, and we need to model cash flows. So we propose a novel econometric approach to extract this persistent, slowly time-varying component, and also higher temporary components like stochastic volatility and jumps. And so we have three components here: jumps, a slowly mean-reverting process, the mean, and some SV. And we will see in a couple of slides why those three components really are needed for addressing these issues. Contribution of this work, we provide a new cash flow measure that can be used to empirically test asset pricing model at daily frequency. And think about all this variance decomposition of good beta, bad data. They've done them at lower frequency, right? Annual data. We try to find a way of dealing with these things at a higher frequency, daily. We can do that. We develop a Bayesian approach for estimation and inference on the various model components. So we will have a model of dividend growth with different components, and we can have inference on all of each of the components. And another thing we can do in this paper is we analyze the timing of cash flow dynamics, and we relate that to traditional measure of dividend growth and macroeconomic variables. And there is a bunch of papers here. John Cochran has all this, the Dr. Didenbark paper showing that dividend growth is not predictable, and there are a couple of more recent papers by Jules and Ralph, and by Seth and Brian that shows that once you filter out some noise components, you do find predictability. And the last thing, we are able to explore the importance of daily cash flow news in explaining and predicting stock returns at the aggregate level, and also cross-section. Okay, so that's the scheme for today. Right, just to give you a preview of results, the persistent component, the mean of the dividend growth process, is significantly and positively correlated with aggregate stock market returns. So cash flow news really affect, to an extent, aggregate stock market. It also predicts aggregate dividend growth, a realized one, better than state-of-the-art method, which are lower frequency, like the Jules and Ralph one. And it also predicts macroeconomic variables, like GDP and consumption growth. Now, in the paper, we also have a kind of a more comprehensive model that links cash flow dynamics and stock returns dynamics. And with that model, we are able to make some inferences and some hypotheses and test them. So we see that positive news about the persistent cash flow growth, so basically the difference between the persistent mean today and tomorrow, take the difference, that's the cash flow news. That's, when it's good news, stock market volatility goes down. Good news, market are calmer. Lower cash flow volatility is also associated with lower stock market volatility. Means if in general there is less uncertainty about cash flow, so stock market react to that. And the last key thing is negative jumps to cash flow. Think about earnings or dividend cut, or Citigroup during the financial crisis cutting earnings and dividend announcement. Realizes an increase in the probability of a jump in stock returns and also an increase in stock market volatility. Lastly, we can relate cash flow news to cross-sectional factors used in the literature, and especially we find that it's positively related to market size and firms with weak profitability. So small firms and weak profitability are very much impacted by high-frequency cash flow news. Okay, data and econometric model. So we start by using ordinary cash dividends declared by firms with common stocks on the usual NYSE, NASDAQ, and Amex until 2016. Now, when we talk about ordinary cash dividends, for those of you who are familiar with this data, if a company announces an extraordinary dividend, let's say a big payout in a year, that's still accounted as ordinary cash dividends increase, so that would still be in our sample. An M&A dividend is not going to be there. We focus on initial announcements, which, as I told you, is one of the differences between our work and just the previous works. And on average, this is something I think interesting, dividend announcements precede the actual payment, the ex-dividend payment day, by around 42 days. And then what we do, we define aggregate year-on-year dividend growth measure on every year on day S. And by simply taking an indicator function of the dividend paid by firm I in that day divided by the same firm I paying the dividend on a similar day kind of the year earlier. And then we aggregate in this way. Okay? Couple of graphs to give you the intuition of what I'm really talking about. So this is the time series distribution of dividend news within the second quarter of 2014. Forget about this blank thing. It's simply the second quarter ends in June, so this is basically the end of the sample. And you see that basically almost in any day on the second quarter of 2014, there is some firm, or a lot of firm, around 68 is the maximum here, I think, announcing dividends, okay? So there is, of course, you see some clustering is known, is the earnings season, and that's what we're trying to do, is finding a way of aggregating this information at daily level. Same things for daily total dividends, so we simply sum up on every day the amount of dividend announcement, and you see there is some heterogeneity as well. And then we construct every day a daily dividend growth rate by using the expression I just showed you. And this is basically going to be our daily dividend growth measure. And by construction, this is an annualized one, right? Because we're looking at year-on-year changes. This is how our series looks like. Okay, this is the log, of course. three important things I want to highlight. So there is a thick blue line in the middle, and this is evidence for some persistent component that is what really driving this dividend growth process. And then we see a lot of jumps, spikes, and of course these are, someday a few firms announce very good information, and that's the spike where it comes from. And then we see also some clustering, for example, during the financial crisis where the dividend growth becomes negative, and this clustering is also potentially be addressed by using a stochastic volatility model. So from this graph, you see that we need all three components. One more thing, this graph is plotted again here in the top panel, and we compare that to the standard, let's say, crisp top-down approach. So what we usually do, we take the crisp returns and we extract the dividend series by taking the difference with the with and without dividend return and multiplying by the previous period price level. And then what we do here, we construct, using crisp dividend extracted, crisp index dividend extracted data, a year-on-year crisp dividend growth. As you can see, this is basically today divided by 252 trading days last year. Okay? And every day we have that. This is pure noise. And this is probably why in the profession we never use daily cash flow growth, because this series is pretty much unusable. Okay? So bottom line, the econometric specification I'm going to discuss in a bit should account for all these features. And this is the specification. So we have a mean reverting stochastic volatility model with jumps. So here is the actual realized dividend growth. There's a persistent component, there's a jumps component, and the stochastic volatility component. We assume that the persistent component follows a usual AR1 mean reverting process. And then we also have the probability of a jumps in cash flows, which is a function of the number of firms announcing dividends, right? So the idea here is the following. You might think that in a day, there are 3 firms, one of those 3 firms does a really big announcement, the jump probability should be higher. If you have a lot of firms, basically there's a diversification effect, you shouldn't see that. So we expect this to be negative, and we will see that in fact is the case. Stochastic volatility as usual is the log stochastic volatility. And okay, this is the model. We need to estimate this model. Now, note that unfortunately, this is a latent state. This is a latent state as well, right? So there are a bunch of things you don't observe. You cannot just do a reduced form. We need to estimate this model. The way we do it, we use a standard Bayesian approach by using a Gibbs sampler augmented with a bunch of Metropolis-Hastings steps for the parameters where we don't have a closed form for the conditional probability density function. Okay, and then we also use some tricks like a band sparse algorithm to improve the convergence and the estimation. We work with standard Koenig priors, and we'll very uninformative priors, except for the persistence parameters, but we will see that on a daily frequency, you would expect them to be very persistent, and this is exactly what we find. So here is the estimation results. 2 sample periods, 73 to 27. The reason is only data availability. I'm not going to discuss this now. But in general, I will focus mainly on this post-73. Just one parameter of interest, really, 2. First is the mean of the dividend growth process is around 8.4% per year. This is basically a daily annualized measure. And if you do that, if you extract the same series using CRISP, you see it's, I think, around 7.9%. So it's very consistent with the raw CRISP series, this one I'm talking about. So we're picking up the right thing. And then the second thing, the lambda 2 was the parameter on the number of firms as negative, as I told you, should potentially be expected. Okay? Now, empirical results. Once we estimate this model, what do we get? So this was the original series. Now you might think that jumps and stochastic volatility are not really important. We don't really care about them. So we estimate a model just with a time-varying mean, and that's what we see. This is NJ stands for no jumps and no SV. And what we see is basically the same. So the modeling, the estimation procedure incorrectly will attribute these jumps and SV component to the mean, okay? So there is no improvement. You really need those other 2 components. Once you have them, you get the last bottom panel. And this is a nicely behaved, moving slowly, because it's very persistent. But this, is pretty much picking up the right things. Like the financial crisis becomes negative, as it should. The expected dividend growth during the financial crisis should be negative. And then it bounces back as soon after, I think, mid-January, mid-2010. is exactly what happened. The confidence was raised after that period. Okay, now of course we also estimation of jump probability. So every day we know whether there's a jump or not, and the jump size. Now this jump seems a lot, but I can tell you they are uncorrelated, basically day on a day. And jump size can be of course both positive and negative. Just to give you another piece of evidence for why this is doing, I think, something nice. Here, what we do, we're trying to plot the jump intensity versus the number of firms announcing dividends. So we basically take the median and the 17th percentile and the 25th percentile of firms announcing. And you see here that basically the more firms announce, the left-hand side, the lower the probability of a jump is. Okay, the mean is basically here every 200-something days, while here when very few firms announce, the probability of observing like a jump in cash flow is basically around once every 33 days. And another way of seeing this, what our filter does is every day allocating the realized dividend growth from announcements into a persistent component, a jump component, and the SV. Now, during the financial crisis, as you can see, the red dot is basically the actual number. And the filter in the 8th of December 2009 will give most of the variation in that to a jump component and a little bit to the stochastic volatility, and pretty much no variation in the persistent component. So it was all about noise and not really impacted the long run mean of the process. While in August 2010, for example, the actual realized dividend growth based on announcement of dividends is split between the persistent component, the blue bar, and some SV. Okay? So that's pretty much what every day we have something like this. Now, we have this new measure. We have the decomposition of this measure in different components. The question is, can we predict standard measures? Okay? So most studies, as I just mentioned, extract aggregate dividends from CRISP in this way. And then most studies like John Cochran paper and Jules and many others just run predictive regression. Okay? So we do the same. We run a predictive regression on actual realized dividend growth from CRISP next year by using some lags for accounting for autocorrelation and the standard dividend price ratio, lagged, and our measure of the persistent component the previous period. So TT means that the same, they were comparing apple to apple, so this would be, if this is annual data, will be the last day of the previous year, okay? And these are the results. So we've done both quarterly, 4 quarters rolling versus annual, in both periods from the original period to the most recent one. I will just focus on the first column. What we see is that the persistent component, which you can always see that as the conditional expectation of dividend growth, right, is pretty much predicting the actual realized CRISP-based dividend growth, and the R-squared, this is what I would focus on. So most of this variation is in 1/3, about that quarterly and annual frequency, comes from not the dividend price ratio. As we know, if you just run a dividend growth predictive regression on dividend price ratio, you basically get a 0 R-squared. And it's not even coming from these lags. Most of the variation comes from these two. And I will show you some more results on this thing in a couple of slides. So, and it's also known that it's significant in both cases at the annual and quarterly frequency. Now, predictability of dividend growth has been studied a lot in the literature. John has this paper on little or no dividend growth predictability. Jules and Ralph, basically by filtering out using the Kalman filter, this the persistent component, find that there is some predictability, so there is some time variation in dividend news. And the same was found by Seth and Brian. And what we do is, okay, the only difference is that those measures are at the annual frequency and at monthly frequency. What we do, we compare our measure with theirs, and the idea is that our measure is daily, right? So it uses information at a much more granular level. So we should be able to picking up any variation earlier than those methods, right? So what we do is the same. Now, this plot shows you the actual realized versus the Jules measure and the Brian and Seth measure. And you see that our measure is the red one, and it's always usually a bit ahead of the yellow bar. So it's always picking up variation and this persistent component just before the other, simply because it's timely updating, right, by using daily information. And of course, it's also important to know that during the financial crisis, the actual realization is very negative, and our measure is trying to get that as close as possible, right? So it's closer than the yellow bar. Well, this is a graph. We can formally test it. How we do it, we run basically predictive regression using these two variables, our mu dt and the measured by Jules, Ralph, and Seth and Brian. Monthly will be the Seth and Brian, annual will be Jules and Ralph. And what we see is that, if you just run a regression of dividend growth on their own measures, this is pretty good. It's 14% variation, 13%. This is consistent with the results in their paper. We replicated both of them. It simply means there is some dividend growth predictability. Okay? Once we just use our measure, we see that there is much more, because probably we're simply timely updating using more information. And then when we plug them together, we see that both measures are still very important, so they're not completely subsumed each other. And the R squared jumps to around 44%. So again, you have to keep in mind the standard number is 0%. Now we are 44 once we include both measures, or even 30 when we only include one. Okay? Now we're going to do some formal test, a forecasting encompassing test, basically telling me whether our measure is somehow completely encompassing the others, and what the results show is that both measures are still important, although our measure is slightly better, and the reason is it uses more wisely the cash flow news information. All right. So this was for dividend growth. We can also relate to economic activity and simply run a standard predicted regression at quarterly level for consumption growth and GDP. And you see, again, most people would see that the consumption growth is not predictable, and these are the results. So around 1/4 of the variation in both GDP and consumption growth quarterly level are explained by cash flow. So the idea is that dividends and cash flow in the economy really matter also for aggregate macroeconomic quantities. And I will give one more information about this at the end of the presentation. Okay, so this was a model only for for cash flow dynamics. Now what we can do is we can have kind of a structure model, let's say, or more precisely, a more comprehensive joint model for stock returns and cash flow dynamics. What this model is simply using the standard way of modeling returns in high frequency done in the equity literature. So you have a time variation in the mean, jumps, and stochastic volatility. But in addition to that, we can add this part here, or these betas, which are basically telling you what is the spillover effects from cash flow to stock returns, right? So whether the mean as in cash flows, or the change cash flow news here basically is impacting stock returns, whether the stochastic volatility of cash flow is impacting stock returns, and whether jumps in cash flows are impacting stock returns. We can estimate this model. Of course, as you can see, is kind of complicated model to estimate. So, and it's very time consuming as well. So anyway, we estimate this, and we also add an additional step by having the probability of a jump in stock returns be not only a function of the number of firms announcing, but also in the jump in cash flows, right? If there's a good news or a bad news on the cash flow in the market, you would expect that to be somehow impacted also, realizing the probability of a jump in stock return, okay? And the funny and good thing about this general model is that we are able to test some hypotheses, right? So we have 4 hypotheses here. One is stock returns tend to be higher on days when there is good news about cash flow. Okay? Well, temporary shocks should not really matter, right? It's transient shocks that should dissipate and should be not really impacting the mean. So we can test beta 1 greater than 0 and these 3 and 4 equal to 0. We have a second hypothesis saying that stock returns tend to be higher in periods when there is a lot of volatility in cash flow, like uncertainty, and which is basically testing beta 2 equal to greater than 0. Then we have the third hypothesis that the return volatility tends to be higher on days with negative news about cash flows, right? Cash flow news is bad. You expect volatility to spike up, VIX. And also a negative jump in cash flow should result in higher volatility. So these are the coefficient sign we expect. And then the last one is the probability of a jump in stock return is higher if there is little information about the cash flow. So few firms announcing dividends. And if there is a large negative jump in the cash flow process, which in other words is testing whether the lambda coefficient in the probit model here are negative. These are the results. I'm not really going to discuss we don't have much time, but what I wanted to say is that beta 1 is greater than 0 and is statistically significant. Beta 3 and beta 4 should be equal to 0. This actually is slightly significant at the 10% level, while beta 4 is 0. So there is some evidence in contrast to our hypothesis here that temporary shocks somehow matter. But again, maybe it's something we should explore more. And then all the other coefficients, beta 2 is greater than 0. That's the case. And the lambdas and the gammas have the correct sign. Okay? So this was a kind of a structural model. Now we can have a reduced form model, running regression. Okay? What we do here, so to compare with existing study, we simply run contemporaneous regression of returns on the left-hand side on standard measures of cash flow growth or news. Okay? What we see here is the following. First of all, let me back up 1 second. We use t to t plus 1 for the following reason. So this is a 2 days cumulative return. The reason being most of announcements and cash flows are coming after hours. Okay? So if we're looking at the return today and then the news happens at the night, we're basically missing that. So that's why we need to take a RT to t plus 1. So it's a 2 days cumulative. And here we also compare with the dividend announcement days and the dividend payment day. Like the standard literature, we use these numbers here and find nothing because of the payment day. When we look at the announcement day, we find that the change in the persistent component, think about that as a cash flow news, is really important for explaining somehow stock returns. Now, the R squared is very small. Of course, predicting daily stock returns is very hard. So these numbers are quite big, actually. We also have a bunch of extra exercises on volatility dynamics. We look whether the persistent component and cash flow somehow is negatively related as we expect to volatility dynamics. And that's what we find. We find that using VIX, S&P, realized vol, the persistent component is negatively related using state-of-the-art model like this one or just an AR1 process. Okay? Another thing, I mentioned at the beginning that we are also able to look at whether aggregate cash flow news is somehow related to portfolios of stocks, right? So think about risk factors. And what we do is basically running contemporaneous regression of risk factors on our change in mu dt. And you see that the market, this S&B factor and the profitability factors are the ones related to that. What this shows you, this is negative, which means that there is a positive load on the weak profitability stocks. So weak profitability stocks, small stocks, and the market are somehow affected by news and cash flows. And probably those are the set of stocks you would expect to be reacting to cash flow news the most, right? So this is, and another thing I would like to mention is that we don't use any market data on prices when we extract our dividend measure. So that's a completely independent set of data, right? So the fact that using dividends and prices, somehow there is a relationship even cross-sectionally is very interesting, I think. There is a couple of more work in progress that I briefly mentioned because I have 1 minute. We have a real-time measure. So what I showed you is using the full sample, right? In theory, we are able, and we do that, every day to estimate the model in real time. Now, this is very cumbersome computationally, so it takes a lot of time, weeks. But we've done it. And we also tested with the Fed nowcasting model. What we try to see is whether this persistent component and cash flow somehow in real time helps also forecasting GDP growth in real time using this model. And there is some evidence of this. We also are trying to coming up with a present value model starting from the Campbell ratio and decomposition to see where we can estimate this at daily frequency as well. And then, this heterogeneity across industry for cash flow dynamics, maybe yes, maybe no. We try to do that. The problem here is that we only can use few industry because we need data, and if we use too many industries, there is not enough data to estimate the model. But what we see here, and I will focus just on this is the banking sector pretty much, the Farm and French 50 industry, and you see that during the financial crisis, there's a lot of decrease in the expected dividend growth, right? While for consumer goods, the decrease is still not substantial and is still positive, in fact. Okay? So to conclude, we developed in this paper a new methodology for constructing daily estimates of cash flow growth based on individual firms' announcement of dividends. The series, as you have seen, is very lumpy due to firm-specific events and changes in the number and composition of firms announcing dividends in any given days. Another thing I didn't mention is that if you do that with CRISP, the number of firms in the numerator and denominator will be different, and even the firm itself. So it's inconsistent. Our measure is very consistent because we make sure we match in the numerator and denominator the same firms. And what we do, we decompose cash flow growth into this normal shocks, jump, and the persistent predictable component. Finding that the persistent component predicts future dividend growth, as well as consumption growth, GDP growth, and is positively related to contemporaneous stock returns. So by exploring the importance of this daily cash flow news, we find that there is some evidence of that. And bottom line, we think that potentially this new measure has potential interesting application in asset pricing, of course, but also in corporate finance and, of course, macroeconomics. Thanks.